Hello, this is question 9 of the November 2019 paper, Physics Science Paper 1. And this question is about generators. So the question says that a simplified diagram of an electric generator is shown below, where the coil is rotated with a constant speed and EMF is induced in the coil. Okay, so the coil is rotated and the coil is part of the armature. So this part is the armature, and then this around it is the magnet. And we're told that the coil is rotated, so the armature is rotated. Okay, so it now asks us in question 9.1.1, is this an AC or a DC generator? So in an AC generator, we know that the armature stays still and the magnet rotates. So the armature is still and the magnet rotates. And in DC generator, the armature rotates and the magnet stays still. So it said in the question, the coil, the coil is rotated. So the armature is rotated. Now, when is the armature rotated? In a DC generator. Okay, so the answer for question 9.1.1 is DC. Okay, it was only 1 mark, but we need to give the answer. We don't need to give an explanation, but obviously you need to understand the explanation before you can give the answer. Okay, question 9.1.2 says, briefly explain how an EMF is generated in the coil when the coil is rotated by referring to the principle of electromagnetic induction. Okay, so the principle of electromagnetic induction explains how mechanical energy is converted into electrical energy. So we know that how EMF is generated is because the coil is turning, and then we've got a change in magnetic flux, and that generates the EMF. Okay, so when this turn, change in magnetic flux, and then an electric field is generated. Okay, so how can we answer this question? Using the principle of electromagnetic induction to explain how an EMF is generated in the coil when the coil is rotated. So we can say um, an EMF is induced in the coil, yeah, in the coil as a result of change of magnetic flux linked with the coil. So the change in the magnetic flux in the armature, which is linked with the coil, obviously, creates the EMF. So we are using, so the principle of electromagnetic induction involves mechanical energy going into electrical energy, and we are using that principle in this answer. saying EMF is induced, which is the electrical energy. How is it induced? The change of magnetic flux linked with the coil. Mechanical energy is a change of the magnetic flux because we are physically moving the coil. That's our mechanical energy, is us moving the coil. Okay. Then question 9.1.3 asks us to draw a sketch graph of the output voltage versus time for this generator. And it asks us to show one complete cycle. Okay, so we have a DC generator. So we know that, okay, so first of all, so we know that the DC generator looks like this. And we know that the AC generator looks like this. Okay, but this is not our graph. We have to draw voltage versus time. Okay, so our output voltage is on the y-axis, and our time is on the x-axis. Voltage measured in volts and time measured in seconds. Okay, it's just always the voltage on the y-axis and the times on the x-axis. Then one complete cycle is two little bumps. So we draw our two little bumps. We try and make them as similar as possible. And there's our graph. If our generator had been AC, which is not, our graph would look like this. We would have the voltage and volt on the y-axis and the time in seconds on the x-axis. And it would look like this. Okay, so that is question 9.1.3. Now we go on to the second part of the question, which is more of our working out part, okay? And we are told that a 200 ohm resistor is connected to a DC voltage supply, as shown in diagram A. The energy dissipated in the resistor in 10 seconds is 500 joules. Okay, so the energy dissipated in this resistor in 10 seconds is 500 joules. And the energy. It's always good to write out what you have so you can see what you have and what you need. Okay, and then we are told that the same resistor, so it's also 200 ohms resistor, is now connected to an AC source, diagram B, and 500 joules of energy is also dissipated in the resistor in 10 seconds. Okay, now if we go to our question, in question 9.2.1, we are asked to define the term RMS voltage of an AC source. Okay, now this is just learning. You just need to learn the definition of this term. And the definition is the AC potential difference or voltage which dissipates the same amount of energy as a DC potential difference. Okay, let's write this down. So just learning. Okay, and that is the answer to that question. Okay, now in 9.2.2, we are asked to calculate the maximum or the peak voltage of the AC source, which is this one, the pink one. Pink. Okay, and the maximum or peak voltage of the AC source. Okay, so what have we been asked to find? This is why I say that it's nice to write out what you want and what you have. So what are we looking for? The maximum voltage, so the V max we're looking for. We have the time that the energy, the time in which the energy was dissipated, which was 10 seconds. We also have the um the energy that was dissipated. It's 500 joules. And we have the resistance of the resistor was given to us, which was 200 ohms. Okay, so we want the Vmax. We know that the RMS voltage is equal to the maximum voltage over the square root of 2. Okay, so we can see that we need, if we can get the RMS voltage, then we can very easily work out the maximum voltage. Okay, so now we look at our formula sheet and we see what formulas can work for us. So we see this formula, which says the work done is equal to the square of the voltage over resistance times the change in time. Okay, and we know that the what we measure work in is joules. Work is measured in joules, energy is measured in joules. So the energy dissipated, so the energy, what did they say? The energy dissipated in the resistor is the same as the work that is done in the resistor because work and energy are both measured in joules. So, AKA the work done in the resistor. Okay, so what do we have from this formula? Okay, we now have the work done. We want the voltage, we want the RMS voltage, but the no, but we were told that the in our in our previous question, we were asked to find the term RMS voltage, and it was the AC potential difference or voltage which dissipates the same amount as the energy as the DC potential difference. So the RMS voltage is just this voltage here because it's just like the normal measure of voltage that we usually get. It's not the maximum, it's just like the normal measure. Okay, so we have this voltage. We were given a resistance. Oh, no, sorry, we don't have this voltage. We're looking for this voltage. That's what we're looking for. We've been given the resistance and we've been given the time. So now all there is left to do is to substitute everything into the formula. Okay. Of the calculator. Make sure you always write the correct number of zeros that you need. Okay, and then if you do the square root on both sides, then we get the voltage in the circuit is 100 volts. Okay, so therefore, and the voltage is the same as the RMS voltage. Therefore, the RMS voltage is 100 volts. Okay, now we go back to this formula over here that we talked about earlier. We have now found the RMS voltage and we need the maximum voltage. So what do? Please don't write this on the side like I'm going to write it. Please write it underneath. I'm just writing on the side so that everything can be together. In your exam, please write it underneath. Otherwise, the marker might not write this up on this, might not mark this up on the side. Okay, so we take this 100 volts, we put it in here. Two, therefore, the maximum voltage is 141.42 volts. Okay, and that is how we work out this question. So as you can see, it really helps for any question that you're doing with working out, to write down everything that you have and everything that you're looking for and to try and find a formula that has got all of it in. And if you can't find a formula that's got all of it in, you can always find two formulas that have got most of them in and then substitute them into one another. Just try and find something that everything can fit in. Okay, and then in the next video, we're going to be doing the last question of this paper, which is question 10 and the photoelectric effect. Thank you.